Welcome to Accelerated Chemistry. In this video, we will discuss units, prefixes, and significant figures that convey precision in our measurement. Every physical quantity is measured in its own units in comparison with a given standard. These standards are in no way special, as in the sense that they have absolute priority over others. They have been defined according to their convenience and are used, like with any defined unit, as a relative comparison to measure other things. Most scientists in all countries have for many years used the metric system. In 1960, an international agreement set up a system of units called the International System, or the SI system. This system is based upon the metric system and units derived from it. The fundamental SI units are listed below. Now, a ratio of units that is equal to each other is called a conversion factor. For example, if we take the definition of 1 minute as equivalent to 60 seconds, then if we divide both sides by 1 minute, or if we divide both sides by 60 seconds, the result would be exactly the same. All of these ratios would be equivalent to each other and also equal to 1. Every conversion factor behaves in this manner. The reason for this is that when we use such conversion factors to translate a given measurement, we do not want to use a ratio that is not equal to anything other than 1. If it did not, it would change the value that is to be converted. However, a source of confusion for many students is how to arrange the ratio to convert a given value. The key here is your units. In order to convert 30 minutes into seconds, it is most beneficial for the conversion ratio to have minutes in the denominator, such that minutes will be over minutes and will be equivalent to 1. With seconds in the numerator of the conversion ratio, we understand that we must multiply 30 by 60, and the result will be 1800 seconds. If, however, we use the conversion in the other way, this would not be inherently wrong. It would just yield units that would make things highly impractical. 0.5 minutes squared per second makes little sense. But as can easily be shown, this is still actually equivalent to 1800 seconds. It is important to note that every unit and unit prefix can be treated exactly like a variable of algebra. Provided are a variety of prefixes that you'll be working with throughout the year. The ones in blue ought to be memorized just for their convenience. Finally, it is important to note that a series of conversions can be performed in succession to one another, such that the multiplication and/or division can all be done at once in a clear and concise manner. Finally, with measurement, we must also consider the possibility of error. Accuracy is labeled on the vertical axis in the figure, and like precision is a concept. The measure of accuracy is systematic error. The idea is that a measurement is accurate when it is aimed squarely at the center of the target. A pipette or automated liquid handler, which is accurate, will deliver on average a result which is close to the center. As shown in the upper left target of the figure, it is possible to be accurate while also having poor precision. Accuracy and precision are independent of one another. Each can be increased or decreased without changing the other. Precision, however, is a concept meaning that results are tightly clustered. Precision can be achieved regardless of where the cluster falls on the target. The degree of precision can be measured by quantifying the overall effect of all random errors using descriptive statistics such as standard deviation, relative standard deviation, or coefficient of variation. Precision is necessary for achieving truth, but it is not sufficient. Truth requires both precision and accuracy. Trueness is a combination of accuracy and precision. Trueness requires good accuracy and good precision. Trueness is measured and reported as an uncertainty. Uncertainty is frequently presented in a very mathematical way, with lots of equations. But it is helpful to remember that uncertainty is simply a quantitative expression that tells us the trueness of the measurement. The manner in which precision is conveyed in measurement is through significant figures, the very numbers that are written when portraying the value of the measurement. Non-zeros always carry significance, but zeros before non-zeros are never significant. Zeros in between non-zeros are always significant, but zeros after non-zeros are significant if and only if there is a decimal present. Finally, exact numbers do not affect significance. These rules would be particularly important when problem solving. For when you have completed the entire problem, your result should be reported to the correct number of significant figures. After a series of calculations which involve multiplying and dividing, you should round to the least number of significant figures. After a series of calculations which involve addition or subtraction, however, you should round to the least number of decimal places. Till next time when we consider the mysteries of the absolute, Crip.